and welcome to this series of videos which I am calling as EENT. And what I mean by that is ENT is a very popular abbreviation for elementary number theory, and I'm hoping to get you started with some very simple facts, and therefore I should call it as elementary number theory. And the first thing that comes to my mind is to talk about prime factorization, and this is something that we all know well, but let's look at some examples. For example, you take any number and you can break it down till you're left with only primes. For example, 24 can be written as 2 cube into 3. Let's take another example, maybe 52, and this can be written as 26 into 2, and this is 2 square into 13, which is a prime. 100, of course, very popular, 2 square into 5 square. Let's take another example, maybe 360. This can be written as 180 into 2, and this is 18 into 2 into 5 into 2, and this is equal to 9 into 2 cube into 5, and this can be finally written as 2 cube into 3 square into 5 raised to 1. So let's write this down in a symbolic form. You take any number n, and this can be broken down into a product of primes, which can be increased, maybe in increasing order, and this product has to end somewhere. So okay, right, and now for example, in this example we can say that p1 is equal to 2 and p2 is equal to 3 and p3 is equal to 5, and it ends at 5. Now some of the primes can be repeated, so for example 2 here is repeated 3 times, so I shall write the exponent as k1 is equal to 3 and k2 is equal to 2. In this case it's 2, and in this case k3 is equal to 1. It's the exponent of 5, and so the theorem can be written as any number can be broken down into a product of primes, and some of these primes can be repeated, and we shall just give them the symbols k. So far so good, but I've forgotten to mention the key thing about this fact, and that is that this prime factorization or prime decomposition is, and it deserves a really special word, unique, meaning that all of us, when we set about this task of prime decomposition, get a unique answer. Now this is a nice fact, but is it really useful? And that's really not a great question, because just about everything that we do in number theory will often utilize this fact in the background. Everything we do in problem solving in number theory often will use this fact. So this is so important that it is in fact called the fundamental theorem of arithmetic. So what we've just stated really is the fundamental theorem of arithmetic. So if indeed it is, then of course it has a proof, and what I suggest is you look the proof in some standard number theory textbook, or since you are looking at it for the first time, might be nice to look at article, popular science article, and none better than Quantum. There is an article in Quantum that just fits the bill perfectly, and the author is none other than Vaguten. Vaguten is the pen name of two great Russian mathematicians, Vasiliev and Gutenberg, and they have an article in Quantum which will have all the proofs of the so-called elementary ENT, including the fundamental theorem of arithmetic, and we have included the reference to this article in our YouTube header. So let's take up some examples, and I do not want to ignore the key examples in a book that we strongly recommend and we will strongly follow, Mathematical Circles. So mathematical circles, in fact I am guided by mathematical circles in making these videos on ENT, and this is the first thing that the authors Forman and co talk about, and there are several examples on page number 20, 21, 22, 23, which are not so, some of them are not so easy, some are easy of course, which tell you the use of the prime factorization theorem in problem solving. Okay, prime factorization theorem in the fundamental theorem of arithmetic in problem solving. I do not want to neglect the first example itself, and that is going to be, I'm going to take it up. The first example is simple, but I think it's so important that it's worth discussing. And the question that is being asked here is, there is a number, let's call it capital N, and the capital N happens to be 2 raised to n. The prime factorization has already been done into 3, and there is another number small n which is 2, and the question being asked is, does n divide n? So I'm using the standard symbol to ask whether capital big number n is divisible by small number n. So, and in this case the answer for this question is yes, and the reasoning goes like this. The prime factor of small n, which happens to be 2, does occur in capital N. So let's write this down a little bit more explicitly. First we define what you mean by divisibility. It's an important definition. If n divides n, we mean that there exists, capital N can be written as n times some number k. We don't really care what k is, but it can be written as n times k, and this implies that n divides n. So in this problem we are claiming that small n divides capital N, and this is very believable. In fact, let's write it down explicitly. So what we are saying is n is equal to 2 raised to 9 into 3, and n divided by n is 2 raised to 9 into 3 divided by 2, and this can be written as 2 raised to 8 into 2 into 3 divided by 2. The 2 gets cancelled, and what remains is the quotient 2 raised to 8 by 3, and this implies clearly that capital N, which happens to be 2 raised to 9 into 3, can be written as small n times k, which is basically 2 times this number, 2 raised to 8 by 3. So this part is highly believable. What is it? What is the fact? That if the prime factors of n appear, all the prime factors, okay, maybe I should put the word all the prime factors of n appear in capital N, then n divides n. Very acceptable. But the second problem is also looks simple, but it's slightly different. So the question is 2 raised to 9 into 3 divisible by small n equal to 5, and this is capital N. So the answer here is no, and so what we are saying is that n does not divide capital N, and the reason is that the prime factor in small n, which happens to be 5, does not appear in the prime factorization of capital N, which in this case happens to be 2 raised to 9 into 3. So there is no 5 is a prime factor in the prime factorization of capital N. So let's see, what are we trying to prove? So if the prime factors of n do not appear in capital N, then n does not divide capital N. So how does one prove this? Okay, how does one prove this? And what are we trying to prove? Maybe should worth writing it down a little bit clearly. N does not divide n if the prime factors of small n do not appear in capital N. So this is what we're trying to prove, and let's try to prove this. So if, and this is this is a 2 or 3 line proof, if n divides n, this implies that capital N is some multiple of n. Okay, now the number in the left hand side is equal to the number in the right hand side, right? And this implies that all the prime factors in the prime factorization is same on both sides, and this is due to our fundamental theorem of arithmetic, and this implies that the prime factors of small n appear on the left hand side, which is capital N. So that's it, QED. Just want to point out the role of the fundamental theorem of arithmetic in this proof, okay, in this proof, right? And this is a fact that we use now, it's embedded into our thinking, but it's good to know that we are confident that this is all fine because of the fundamental theorem of arithmetic. Now, before I close this lesson, I shall include 2 problems from a much tougher book. It's not the beginner's book, I think, but nevertheless one of the popular books, Winning Solutions by Lozansky and Rousseau. I think they are mathematicians who were involved with the Olympiad movement in America, and obviously it's a very nice, wonderful book. So I shall pick up the first problem on the example on page 3, and the example goes like this. Very interesting example. I suggest this as an exercise. Find all primes P such that 17p plus 1 is a perfect square. Okay, so as a hint, I suggest think along the lines of factorization, and I'll just give you the answer. Answer is only p is equal to 19 fits the bill. You can prove that there are no other solutions, but my suggestion for this problem is the role of our fundamental theorem of arithmetic. Okay, right. So please do attempt this problem, and you can also check the solution on the book on page 3. On page 5 is another interesting example. I'm not even going to state the example, but somewhere towards the end the solution reaches this stage, and that's where I want to pick up. So one has to find 3-digit numbers A and B such that 5999A is equal to 994B. So let's see how the solutions proceeds from this stage. It's very interesting. So first of all, notice that the GCD, the greatest common divisor of 5,999,994, you could use Euclid's algorithm and zoom down on the GCD, and it happens to be 7. So 7 clearly divides both sides, and when you divide both sides by 7, you come to a new equation, which is 857a is equal to 142b. At this stage, there's a simple but very interesting move. Notice that the GCD of 857 and 142 is equal to 1, and that means follows from here. And that means that there are no common factors between 857 and 142, but the two numbers on both sides are same, and this implies now this is a big step. This implies that all the prime factors of 857 are in B, are available in the prime factorization in B, and this implies that 857 divides B, but then B is a 3-digit number, so this implies B is equal to 857, and that quickly implies that A is equal to 142, and that's the end of the problem, right? So I think I have introduced you to one basic theorem in ENT, and we have a few more coming up in the next few videos. See you. Bye.